we're now going to discuss the effect that the fuselage, nacelles, and stores can have on roll stability. So let's start with the fuselage, and I'm just going to do some simplified drawings here. So here's my fuselage, and let's start with what's called a high wing configuration. So that means that your main wing sits above the fuselage. Now let's put this into some side slip, and we're looking at the back of the aircraft. So positive side slip would be the aircraft moving to the right here. And so what happens is there's the flow, we have some velocity now that's coming in. So the aircraft is moving to the right, which means that the velocity is coming in from the right wing here. And so what happens is the flow has to get around the fuselage, or that component of velocity has to get around the fuselage somehow. And so we get some, so if we were to just draw streamlines of this flow kind of going around the fuselage here, we see that on the right-hand side of this aircraft, we get some component of flow that increases the angle of attack on the right wing, and we get some component of flow that decreases the angle of attack on the left hand, or on the left wing. And so that, of course, creates an increase in lift on the right-hand side and a decrease in lift on the left-hand side. So this would be a change in lift due to that side slip. Okay, so for positive beta, we are now going to create a negative rolling moment. All right, so a high wing is stabilizing in roll. It creates a negative rolling moment. And we can now look at a low wing configuration. That means that the fuselage sits above the main wing, and we actually get the opposite effect. So we'd get streamlines now that do something like this. And so on the right hand side, again, if we're looking from the back of the aircraft towards the nose of the aircraft, on the right hand side we get a decrease in lift, and on the left hand side we get an increase in lift simply due to that component of velocity that's induced by that flow needing to go around the fuselage. Okay, so our delta L on the right hand side would decrease, and our delta L on the left hand side would increase. And so this would create actually a positive rolling moment with positive side slip. So a high wing is stabilizing, and that's equivalent to roughly 2 to 3 degrees of dihedral. Okay, if you have a high wing, that's roughly equivalent to 2 or 3 degrees. If you have a low wing, that's roughly equivalent to 3 to 4 degrees of anhedral. All right, so on fighter aircraft, and on older fighter aircraft, I should say, like the Spitfire and the P-51 Mustang, you see these low wing configurations. They didn't want to have they didn't want a lot of roll stability. So what you'll see is on low wing aircraft, generally they will have more dihedral to counteract the anhedral that they're getting from from this configuration here. So this is naturally giving them some anhedral effect, and so you'll generally see aircraft have a little bit more dihedral if they have a high fuselage, or excuse me, a low wing, and sometimes it's actually not. You'll even see aircraft that have a high wing that then put in some anhedral to counteract some of the dihedral effect due to the fuselage here. Remember, that's giving them 2 to 3 degrees of dihedral, and so sometimes you'll even see some anhedral here on high wings. One example of that is actually the Antonov. The Antonov 225. This is a very large aircraft with a very large fuselage, and so if you look here, let's look at this image here. This is of it sitting on the runway. This is a high wing configuration. You can see that fuselage is massive, and so that's creating quite a bit of dihedral effect because it's a high wing, and so they've actually built in some anhedral into the wing. Now, of course, this is sitting on the runway, and so those wings aren't carrying lift right now, and so of course we're going to have those wings will deflect upward just a little bit in flight, but you can see from these other images that even in flight, this aircraft still has some anhedral, okay? And that what they're trying to do is get rid of that, or part of that is due to the size of the fuselage and the dihedral effect they're getting from that. Okay, so that's an example of what's happening here with the fuselage. Let's look at some external stores now. So so let's say that our aircraft is here, and I'm just going to put the fuselage here right in the middle, just so we can denote the center of the aircraft. And now let's put some nacelles or fuel stores or whatever we're carrying. Could be armament or something that's sitting on the wing, and look at how that affects it. So let's start by putting something right here. That's a very common place to put an engine. And so now let's put that in some side slips. So we're going to have some velocity coming in from the right hand side. And now let's just look at, let's neglect the fuselage and just look at the flow caused on these wings by the flow needing to move around this nacelle, okay? So the flow is going to do something like this, all right? So we're going to get an increase in angle of attack here out of the wingtip. We're actually going to get a decrease in angle of attack closer to the center of the aircraft. And then on the left-hand side, we're going to get an increase near the center and a decrease out at the wingtip. So we're getting an increase and a decrease on both sides, but what's important here is the moment arm of, or the locations that are increasing and decreasing. So you can see out of the tip, we have an increase and a decrease. Those have the largest moment arm. And then inside here, we're going to have some component of that that's being kind of counteracted, but those have a smaller moment arm. And so this is going to be dominated by the effects out here at the tip. And so this will actually create an increase in delta L on the right-hand side and a decrease in delta L on the left-hand side. So that creates a negative rolling moment. And so that is stabilizing. So if those nacelles are sitting beneath the wing, part of the way out, that's stabilizing. Let's actually move those out to the tip now. Okay, so let's draw another aircraft here and move those stores out to the tip, and then draw again the velocity moving around those. And you can see here, so we're going to have actually a decrease in velocity here, an increase in velocity here. And out beyond that store, it's not affecting the main wing because there's no main wing out there, right? So so this is actually a destabilizing effect. We're going to have a decrease in lift here and an increase in lift here, or increase in delta L right there. Okay, so that's destabilizing. So this was, let's just write this here. This is stabilizing in roll. This is a destabilizing effect, okay? So the position of those nacelles or engines actually matters. You don't necessarily want them out at the tip if you're hoping that they will give you some stabilizing effect. Now, sometimes you see aircraft that do carry stores out there, and those are destabilizing. So I mean, you can mix and match these effects here to get whatever roll stability you're looking for. Let's look at two more examples here. Let's look at the same aircraft here, but put these stores on the upper side of the wing. Okay, so, or the engines or whatever it is, and then again we'll draw the flow moving around those, and we see that we get a decrease there, an increase here, a decrease there, and an increase there, right? So again, this is the same as this example over on the left-hand side. We have some portions that are increasing and some portions that are decreasing, but what's important is the moment arm associated with these. So the portions that are dominating this are out at the tip. So we have a decrease in lift out on the right-hand side, an increase on the left-hand side, and so that is giving us a delta L that's positive over here and a delta L that's negative right there, and so that's creating a positive rolling moment, and so that is destabilizing. And finally, we can look at this example down here, and simply move those stores up to the top, out of the winglets, but on the top. And we could do the same thing. So the flow is moving around like this. And we'll see that over here we get a decrease on the left hand side, and on the right hand side we get an increase. And so this will create a negative rolling moment, and this will be stabilizing. Okay, so these interactions are difficult to predict in a really simplified manner, to really measure how much roll stability these are going to create. But what's important here again is qualitatively to understand what these locations are doing to the stability to the roll stability of your aircraft. Although quantitatively, we really need to get this from CFD or wind tunnel or something like that to really predict the roll stability.